Hello, this is Peter Newman with part 4 of the tri-bucket analysis, and in this video we're going to do some work with engineering data. So we go to the workbench program, and on the project page we double click on engineering data and a second tab opens, and we can define a material. You say type the word sand, and if we want to use a specific geomechanical material model like more Coulomb, we drag and drop that, and then we type in the values for this material model. I'm no expert in geomaterials, so I'm going to leave sand out of this and just define a material called soft or soil, and it's going to have a linear elastic property, and I only need two values for linear elasticity. Steel has 200 gigapascal of modulus, and if I want to be much softer than that, I can be 2e to the 9, for example, with a 0.3 instead of 2e to the 11 for steel, so I'm 100 times softer than the steel. And that's the material I'll use. I'll leave soil for someone else to tackle. Once you've added that material, it wants to refresh, and that brings that material down into the model, and then in the model we have the ability. The buckets are already structural steel, and since they're sheet bodies, the shell elements will have a 25mm thickness. But all the soils, you can click and control and shift click all the soils, and in one go change from structural steel to soil. So we have assigned a softer material now to the soil and the buckets are all steel. So let's get into the rest of the setup for solving. It's always good to do a default mesh, so let's just look at that, and it's generally going to be fairly coarse, but it might be adequate to see if the model at least starts to run. To get the model to start to run, there's a few settings. You click on analysis settings, and auto time stepping is always good to turn on, and initial substeps 10 is a good place to start, and the maximum just should be 10 times larger than that. Pretty much always have large deflections on for nonlinear problems, and since we have a force, and I just made up a number of 100,000 newtons, if I actually want 5 times more than that, I can take the solution at the end of this amount and keep going from the last point instead of solving over again by setting the restart controls to manual and telling it to retain all the files at the end of the solve so I can go further. That's quite useful. And we have one more setting, which is this solution information, and set the Newton-Raphson residuals to 4, and I'll show what those look like at the end. This is very useful for troubleshooting when convergence fails, and I did think about one change I wanted to make. On that remote force, there's a setting for the behavior, and it's either deformable or rigid, and why I actually want rigid. So I want rigid elements coming down to the faces of these tops of the buckets and causing them to tilt. Actually, I think if I added the 3 faces on the sides of the bucket, then the bucket itself would become rigid. Let's just see what happens from here. So we're ready to solve because we've done all the correct analysis settings, and we'll hit solve, and I'll show you what we'll see. And the thing we can do is click on solution information, and the output from the solver will start scrolling past in this window. And solving often takes some time, so we would stop the video and we won't wait for the whole thing. But here it's scrolling past, giving you information. The information scrolls by a bit too quickly, so you can say put in an update interval of much longer, so you can scroll back and look at what it was typing out in here. And it just has the units that you're solving in. I probably should have changed to meters, but it can solve this problem. This is just a first look at it. Total number of nodes is 32,635. So the student license limit is 32,000 nodes. So this mesh would not solve on a student license, and it's very coarse. We need more elements to get good results. So this is a problem that is only going to be useful on a research or a full license with unlimited number of nodes. We're going to scroll down. There's the type of element it's using. There's the contact information for the different contacts that were defined. And then when it gets ready to solve, I have 8 cores on this computer dedicated to solving this model. It's not very balanced, so it won't solve 8 times faster than 1 core, because it's not super well balanced due to the contact. And there's the different elements, and here's how much memory it needs to solve. So it needs just a bit over a gigabyte of memory, and it's solved. So the other thing is we can look at the force convergence plot, and here it starts with 1/10 the load, and it took 9 iterations to get the force imbalance in purple to go below the balance criterion in cyan. And when it does that, it increments the load from 10% to 20%, and now takes some more iterations to get to the next increment of load. At 20% this is converged, and then 30, 40, 50 and 100%. It's completed the solution, so we can go and look at, say, the total deformation and